So the discovery of the neutron, which we may know about, is not as exciting. But essentially, it's there to make it's how they found out the different masses of all of these. It came out through those experiments trying to find the mass of the proton and how it wasn't adding up, which we'll talk about here in a second. So from these experiments, and trust me, there are many more experiments that were used to reason and find out all of the information about the atom, and it's still something that we're not perfectly 100% sure on. We can now say that the atomic structure is made up of the nucleus, which contains nucleons. Okay, so those are the particles in the nucleus. The two particles in the nucleus are the positively charged protons and the electronically neutral neutrons. So pro for positive, nu for neutral, and those are our nucleons, is what we find in the nucleus. Surrounding the nucleus are the electrons, and those have a negative charge. So to show a little bit of this comparison of how big a nucleus is in comparison to the entire atom, it's like taking a blueberry and putting it in the middle of a football stadium. Okay, so in comparison, the nucleus is the blueberry and the football stadium is everywhere that the electrons could be floating around in that molecule, or in that atom, I should say. So in comparison, it's a very large area to how small the nucleus is. Okay, so now that we know where things are in our particle, in our atoms, let's sketch a picture of helium here on this slide. And we want to label each component of our sketch. We need to show a nucleus, we need to show protons, we need to show neutrons, and we need to show electrons. Now a helium atom it has 2 protons, 2 neutrons, and 2 electrons. Okay, so we have to show our nucleus that has 2 protons, 2 neutrons, surrounded by the rest of our particle, or our atom, that has our 2 electrons in it. So, let's see. So we'll have our 2 protons here in the middle. There's a proton, and there's a proton. We then have our neutrons. They are also in the nucleus. So there's our nucleus. We have proton, and we have neutron. Okay, and then surrounding our nucleus, this is not a perfect circle, I'm not an artist, we have 2 negatively charged electrons. So that is what a helium atom would look like. Okay, so when we were talking about all of these experiments, we said we were able to find the charge and the mass of electrons. Later experiments found the mass and the charge of a proton and a neutron and all that stuff. And that's what is highlighted in this table here, is all of that information, the charge and the mass. So we found the charge to be 9.10 times 10 to the minus 28. The proton is significantly larger in its mass. It's 1.67 times 10 to the minus 24, so they're off by 4 factors of 10. And the neutron has about the same mass as the proton. Now, these masses are recorded in grams, so they each have units of grams. But with traditional kind of balances and everything like that, looking at a mass with a factor of 10 to the negative 28 can be kind of difficult. So what scientists came up with is a mass unit that that is accustomed to small masses. So we have atomic mass units, or AMUs. So when a particle is so small, it has a small mass, so we need small units to accommodate that. And that's where we get the atomic mass unit, which we denote by AMU. So our next column here shows us our masses of each of these in AMUs. One AMU is equal to approximately the mass of one proton or neutron. It's kind of these two values averaged together. So 1 AMU is equal to 1.6605 times 10 to the minus 24 grams. So we took these values in grams and we converted them to mass in AMUs. Then looking at the charges, well, we know that electrons have a negative charge of negative 1.6 times 10 to the minus 19. And in order for the entire molecule to be neutral, it has the same number of electrons as it does protons in order to balance out the charge. Therefore, the protons have to have the same charge as the electron, only positive. So the charge of a proton is positive 1.6 times 10 to the minus 19. And a neutron is electronically neutral, so it has a charge of 0. Because when we're working with electrons and protons, we can't split them up. An electron is just an electron, it's not made up of anything else. So what we can do is we can assign it a charge unit and say that one electron has a -1 charge. And the same goes for protons that can have a +1 charge. So if I know that I have, 3 electrons, they would have a -3 charge. And I can find the specific charge by taking 3 and multiplying it by my charge value there. So it's just an easier way to denote that charge, since these are individual particles that can't be split up. So they're always going to have a charge that is a multiple of 1.6 times 10 to the minus 19. Whether that's positive or negative depends on if you're talking about a proton or an electron. Okay, so these charges are measured in units of coulombs, which we show as C, coulombs. Okay, so let's think about these statements. Which of the following statements about atoms is not true? So which one is incorrect? Well, an electrical charge can be positive or negative. The nucleus of the atom contains only protons and neutrons. An electron has a much larger mass than a proton. The mass of an atom comes from the protons and the neutrons in the nucleus, or all of the above. So we may have to look back to our chart to answer some of these, but let's look at our first one. An electrical charge can be positive or negative. Well, we know that we have charge units of +1 and -1, as well as positive and negative 1.6 times 10 to the minus 19. So our charge can be positive or negative, denoting a proton or an electron. So I believe that this statement is true. The nucleus of the atom contains only protons and neutrons. Well, let's go back and look at our picture of helium, where we drew protons and neutrons in the nucleus. I never labeled this as nucleus. Let's label it. So, based off of that, and what we saw here with our nucleus containing our nucleons, which are protons and neutrons, it would be that this statement, B, is also true. Our next statement says an electron has a much larger mass than a proton. Well, we can look at that on our chart here to look at the mass. So the proton has a mass of 1.00, whereas our electron has a mass of 5.4858 times 10 to the minus 4. So let's take that number and let's convert it from scientific notation to standard form. So our -4 tells us that we have to move our decimal place to the left. So we would have 0.0005485 AMUs. And if we compare that to the mass of one proton, it's 1.0073 AMUs. So we can see that the mass of the proton is much greater than the mass of the electron. Therefore, this statement, statement C, is false. Okay, let's look at our last statement. The mass of an atom comes from the protons and the neutrons in the nucleus. Well, this relates to what we were just talking about before, how the mass of the proton, which is very similar to the mass of a neutron, 1.0086 AMUs, okay, is much larger than the electron. Therefore, the mass of our protons and our neutrons are going to have a greater effect on the overall mass of the particle, okay, of the atom, of the element, whatever we're looking at. So, because these are significantly greater masses in comparison to the mass of the electron, this last statement is true, that the mass of an atom comes from the protons and the neutrons in the nucleus and not from the mass of the electrons. So this statement is also true. So our one statement that was not true is letter C. So let's start talking about all the different elements on the periodic table and how we can find out how many protons, neutrons, and electrons they contain. Because with every new element, we have a different number of protons, neutrons, and electrons. So all atoms can be identified by the number of protons and neutrons they contain in their nucleus. Their number of electrons doesn't matter. Specifically, we can identify a specific atom by its number of protons. So when you're looking at a periodic table or some other sort of atomic symbol, we're going to typically see three different things. So this is an example of an atomic symbol. And it is made up of the element symbol. So this is the abbreviation that we use to indicate an element or an atom of an element. And most of our symbols are going to have one or two letters. And we find those symbols on the periodic table. Some of them sound or look like the molecule or the atom that they are, the element that they're discussing. So Mg is magnesium. So they can be easy to remember. Some of them are not as easy because they come from different language origins. So what we call the element in one language is not how it would be spelled in a different language. So an example of that is something like tin, SN, which is element number 51. SN is tin. There's no S in the word tin. So you may see sometimes that the element symbol resembles the element name, or sometimes it doesn't. Okay, so after the element symbol, we have the atomic number, which we denote by the letter Z. So the atomic number tells us just the number of protons in the nucleus, so protons only. The number of protons can be found on the periodic table. And I'm going to show periodic table as PT. So the number of protons can be found on the periodic table. And it's the number in the upper corner of each box on the periodic table. Okay, so magnesium is element number 12. It has a 12 in the top corner of its entry on the periodic table, meaning it has 12 electrons. Or sorry, 12 protons. My bad, sorry. So it has 12 protons. So the number of protons is the identifying trait of an element. Its value determines the identity of that atom. So magnesium has 12 protons. If I change the number of protons, I change the element. So if we change the number of protons, we change the element. So, for example, if I said we went from 12 protons, that's not spelled right. And we changed it to 11 protons, this would no longer be magnesium, it would be Na or sodium, which is element number 11 on the periodic table. Okay, so that's how we can use our atomic number Z to tell us the number of protons in our element. Now the atomic number is a counting number, so there's not ever going to be a half or any sort of decimal place after that atomic number, because there can only be 12 spheres, 12 protons in that nucleus. We can't have half a proton because a proton is a subatomic particle that can't be broken down. Okay, so this will always be a whole number. Next up, we have our mass number, which we denote as A, and that's this top number here. That's our mass number. The mass number tells us the total number of protons and neutrons in an atom. The number of neutrons is the difference between the mass number and the atomic number, which is our number of protons. So if I were to take, let's say that we have 12 protons. In order to get some number, so we're adding in some number of neutrons, I need to get a mass number A of 24, because that's what my symbol tells me, is 24 is my number of protons plus neutrons. I have to then determine how many neutrons there are by taking 24 and subtracting off those 12 protons. So we get our number of neutrons. To be 12. Okay, so we can say that protons plus neutrons is equal to A, the mass number, or we can say that A minus Z, which is our number of protons, is equal to our neutrons. So we can rewrite this expression. We can rewrite this expression to show our number of protons as Z. Now, when we're talking about a mass number, again, it's just a whole number. It is a whole number, it is a counting number, because it's saying I have this many protons plus this many neutrons. And we can't break a neutron down any further, we can't break a proton down any further, therefore these have to be whole numbers. It's like we're counting them. I have 12 protons, 12 neutrons exactly. The mass number, it sounds like mass, and as some of you may know from previous chemistry classes or knowing just some general knowledge about the periodic table, it is not the mass that we find on the periodic table. It has nothing to do with that. We haven't even talked about that, so it doesn't apply here. We'll talk about that in a future lesson, what that mass means on the periodic table, but it is not the mass number. You may notice that the mass number A is very close to the mass that you see on the periodic table, which makes sense because the mass of an element is made up of the mass of a proton plus the mass of the neutrons in that element. So they would be approximately the same. But we cannot take that mass number from the periodic table and round it or anything like that. We have to just count the number of protons and the number of neutrons. Okay, so these are all whole numbers, and they're counting numbers. There's no decimals, there's no halves or anything like that. Okay, so Here we have a summary of what our atomic symbol looks like. So we have our element symbol, which we find from the periodic table. We have our atomic number Z, which is just our number of protons. And we have our atomic number A, which is our protons plus neutrons. Typically, in a lot of our earlier elements on the periodic table, the number of protons and the number of neutrons are equal. That is not always true. There are some elements that have a different number of neutrons and protons in their elemental form, but we're not going to worry about that. We're just always going to assume that our number of protons and our number of neutrons, when we're looking at just what's on the periodic table for right now, is equal. Now, what happens if they are not the same? What if they don't have the same number of protons and neutrons? What do we call an element that has a different number of protons than it does neutrons? Well, this is called an isotope. So, isotopes are atoms of the same element. Same element. So if they are the same element, they have the same number of protons, but they differ in their number of neutrons. So in order for it to be the same element, we have to keep our protons the same, because if we change the protons, we change the element. But these isotopes will differ in how many neutrons they have. So in our atomic symbol that we see, our mass number A is going to change because A is protons plus neutrons, but the atomic number Z is unchanged because that's just the number of protons. So if protons is staying constant, yes, atomic number would stay constant, and mass number would change because P is the same, but N is now different. Okay, so let's look at magnesium again. So here's our first one that we were looking at before. Okay, we have our atomic symbol of magnesium with a 2412. Okay, so we know it has 12 protons and 12 electrons, as well as a mass number of 24, meaning it has 12 neutrons. Okay. Now, in our next column here, this is now an isotope of our original. So its atomic symbol changed, and instead of having 24 on top, it has a 25 on top. We notice that 12 is staying the same, so our number of protons stays the same from one to the other. Our number of electrons is also going to stay the same, because for right now we're going to assume that the number of protons equals the number of electrons. Okay, so however many protons we have in our element, we're going to assume that we have the same number of electrons. Okay, but when we get to our mass number, it's now 25, meaning we have 13 neutrons. So by the definition of an isotope, it has the same number of protons, but a different number of neutrons. So we have the same number of protons, different number of neutrons. The same can be said about our next isotope of magnesium, which is magnesium with a 26 instead of a 24. So again, we have the same number of protons, but now we have a different number of neutrons. And that number is different from what was previously there in our other isotope, as well as in our neutral elemental form. Okay, so atomic number will always stay the same, because our protons will always remain the same for the same element. If we change the proton, we change the element. But if we're talking about isotopes, they have a different number of neutrons and the same number of protons. And for right now, we're going to assume that our protons equal our electrons. So however many protons we have, that's how many electrons we have. So let's practice that. I would get your periodic table out, because you're going to need to start looking for some elements so you can find their atomic numbers on the periodic table. Okay, that's going to be very useful. The periodic table is only going to give us information about the atomic number and nothing else. It doesn't tell us the mass number. Okay, so it only tells us the atomic number. So Sn, this is tin. Now we see here, this is A and Z. Z is our number of protons, so we can find tin on the periodic table by looking for element number 50. So go to your periodic table and look for element number 50. Look for that 50 in the corner of one of those boxes, and you should find tin, Sn. So our mass number, A, is given to us in the problem as 118. Okay, our atomic number Z is also given to us in the problem. We're told that it is 50. So if we know Z, we know the number of protons, we know the number of electrons, and those are both 50. Finally, we have to find our number of neutrons. So what we're going to do is take our mass number, 118, and subtract off our atomic number, 50, or the number of protons. They are the same thing. So we get our number of neutrons to be 68. So I have 68 neutrons, 50 protons, 50 electrons. My mass number is 118, and my atomic number is 50. Now we can express this atomic symbol in a different way, which you may see first in some of our practice that we're going to do here, but you may also see it in your ALEKS homework. So you may also see this referred to as SN with a dash 118, or you would see it as tin 118. So we put this dash and then the mass number because by knowing what that element is, or its element symbol, we automatically know our atomic number, right? Because the atomic number is our number of protons, which we get from the periodic table. Because if we change our number of protons, we change our element. So if we know our element, then we know our number of protons. So if we were given tin 118, we would go to element 50, we would look for tin on our periodic table and see, oh, it has 50 protons, meaning I have 50 electrons and I have an atomic number of 50. Okay, so just that one number on our periodic table can tell us the atomic number, number of protons, and number of electrons. Then we can use the mass number given to subtract off and find our number of neutrons. Okay, so we'll practice that a little bit more here in our practice with some extra problems. So here, our next example is PT 195. So I have A, but I don't have Z. So this is going to be like what we were just talking about. I know my element symbol, PT, meaning I can look for it on my periodic table and find my number of protons, which would give me my Z value. So take a second, grab your periodic table, and look for the element with the symbol PT. Did you find it? Did you find it as element number 78? That's platinum. Platinum. Okay, you're going to want to start to learn some of these elements, their symbols and their names. So PT is platinum. So just by finding that, we know that our number of protons is 78, meaning our number of electrons is also 78. And we can now calculate our number of neutrons by taking the mass number given in the problem, 195, and subtracting off the number of protons, 78, to give us 117 neutrons. Okay, so take a second and pause the video and try these next two problems on your own. Okay, let's come back together and see if our answers match up. So here we have the element with the symbol C, which hopefully you found on your periodic table to be carbon. If you couldn't find it, go to element number 6, because our Z is 6, meaning our protons is 6. If our protons is 6, our number of electrons is also 6. Okay. Our mass number A is 13, so we can use that mass number A to find our number of neutrons. And we take 13 minus 6, our mass number, minus our atomic number, and we get 7 neutrons. So in this isotope of carbon, I have 6 protons, 6 electrons, and 7 neutrons, with an overall mass number of 13. Okay, our last one, SB, might be a little bit tricky to find, but it is element number 51. So that is our Z. Our A is 121. SB is antimony. So another element with a name that doesn't match up to its symbol. Okay, so we found it on our periodic table. We looked in the corner of that entry and saw that we have 51 protons, meaning we have 51 electrons. And since we have our mass number, we can now find our number of neutrons to be 121 minus 51, so we have 70 neutrons in this element, in this isotope of antimony. Okay, so let's do a little bit more practice. So I have a few elements, nitrogen, aluminum, and strontium here in our table, which you also have in your notepad. What I want you to do is fill in all the missing pieces of information. So some of them I give you the mass number, or some of them I give you the number of neutrons. Okay, the rest of it you can find yourself utilizing the periodic table. So take a second, pause the video, and fill out this table. Just a hint, make sure you use your periodic table and find those elements appropriately. Also, assume that these are all neutral atoms, so they have the same number of protons and electrons. Okay, let's come back together and look at the answers for this problem. So, in nitrogen, we were given the mass number. In aluminum, we were given the number of neutrons and the number of electrons. And in strontium, we were given the number of neutrons, which is all the information we need in order to solve this problem. So, we can find the atomic number for all of these from the periodic table, because their atomic number is equal to their protons. Okay, so nitrogen is element number 7, so it has an atomic number of 7. Aluminum has an atomic number of 13 because it is element number 13 on the periodic table. And strontium has an atomic number of 38 because it is element number 38 on the periodic table. If we know our atomic number, we can also find our number of protons. So you'll see that these two rows or columns are the exact same. And because we were assuming neutral atoms and our protons were equal to our electrons, the column for electrons is also the exact same. So if we know our atomic number, we know our number of protons and our number of electrons if we have a neutral atom. If we didn't have a neutral atom, then our electrons would be different than our protons, which we'll talk about here in a second. Okay, so we have 3 columns that we can fill in just by knowing what the element is and looking at the periodic table. Now what we can do is utilize either the mass number to find the number of protons or the number of neutrons to find, we can utilize the mass number to find the number of neutrons or use the number of neutrons to find the mass number. So in nitrogen, we were given a mass number of 15. So we would take 15 minus 7 minus our number of protons and get a value for neutrons as 8. In aluminum, we were given the number of neutrons. We knew our number of protons from the periodic table, so we just have to add those up. 14 plus 13 equals 27. And in our last column, or last row for strontium, we had the same thing. This is a typo here. This should be 38 plus 50, which would be 88. So that's a typo on my key. Okay, so we took our protons plus our neutrons to get a mass number of 88. So let's write the nuclear symbol for all of these. So we have nitrogen is our element symbol, N. We put our number of protons, or our atomic number, on the bottom there, and we put our mass number on the top. For aluminum, we put our atomic number, our number of protons, on the bottom, and our mass number, 27, on the top. And finally, for strontium, we put our atomic number, 38, on the bottom, and our mass number, 88, on the top. So those are our nuclear symbols for each of these isotopes. Okay, let's do just a couple more practice before we move on to make sure we are learning this to the best of our ability, so when we go and do it on our homework, we are prepared. Okay, so our first question asks us to determine the number of neutrons in each isotope. So here's our example that we were talking about earlier, where we're given the element name and its mass number. So based off of this saying carbon 14, we know that this is carbon 14. Carbon is element number 6, so we have 6 protons, and we want to find the number of neutrons. So we're going to take 14 minus 6 to get 8 neutrons in carbon 14. Next up, we have bromine 81. Br is bromine. So take a second and look for bromine on your periodic table. Br is its symbol, and you'll find it as element number 35, meaning it has 35 protons. So in order to find the neutrons, we take 81, the mass number, subtract off the number of protons, and we get that this isotope of bromine has 46 neutrons. Okay, and in our last example, we're going to take these images and we are going to write the nuclear symbol for each of these nuclei. So, part of our nuclear symbol is first knowing the element symbol. So in order to find what element this is, we should count up our protons. So here the blue spheres are the protons. So let's count up our protons first in each of these. So I have 1, 2, 3, 4, 5, 6, 7, Okay, so element 7 is nitrogen. In number 2, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have number of protons is equal to 10. So element number 10 is Ne, neon. That's the symbol for neon. Okay. And then in our last one, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 protons, meaning this is element number 8, or oxygen. So if we know our number of protons, we know our atomic number, so we can put that on the bottom of each of these in our nuclear symbols. And now we have to count up our number of neutrons and add that to our number of protons. So let's take a different color and we'll count up our neutrons. So this will be 1, 2, 3, 4, 5, 6, 7. So number of neutrons is 7. So our overall mass number is 14 for nitrogen. So we put the 14 on top. In neon, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's one hidden there in the back. So our number of neutrons is 11, giving us a mass number of 21. So this would be 21 on top. And finally, for oxygen, we have 1, 2, 3, 4, 5, 6, 7 neutrons. Adding those up, we have a mass number of 15, which we put on the top there. Okay, so I have one more problem that I want you to try on your own. So our last practice with this is an atom with a mass number of 115 has 66 neutrons in its nucleus. What isotope is it? Pause the video and take a second and use your periodic table to try and solve this problem. We know our mass number is 115, meaning we can get rid of 2 of these examples already because they wouldn't have the appropriate mass number on the top there. So now we just have to utilize our number of neutrons and our mass number to find our number of protons. So the difference between those is 48. 49. There we go. 49. So what element has 49 protons? Well, that is indium. I-N, indium.